a continuation of assignment. So we start with question 2. So you'll be able to do question 2 at the end of the day, but not yet for question 3. Okay? That's why the due date for assignment 2 is on the 20th of November. It's up in Moodle already. Just need to click that. You wouldn't be able to submit yet, although you could click on it, but because you haven't learned your topic, that is erotic force vibration. So I've also included practice questions. These practice questions you need not submit. Strongly advise to do. That's my testing marks. So let's start the day by having a look at the work example. And after this work example, you will wrap up your second topic that's on stat force vibration. This question, May 1999, is an exam question. So what is not stated here, right? In 1999, I wasn't there yet, so I couldn't say, please include arrow. Right? So there will be an arrow over there. That is. So this question has got a rigid frame. So this L-shaped thing is called a frame. So if you look at the question, I'll go to the question. It didn't say that the crank has any mass at all, correct? So even though it's sketched in a very thick format, but because they didn't mention any mass at all, so during exam you don't have to raise your hand and ask where is the mass. I'll just come to you and say, please read the question. That's all I can say. So there's no mass. And this whole L shape is a rigid body. So this joint over here, while it will pivot over there, but this L shape does not deform. So you maintain that sort of L shape. And in the question, you're given quite a few things. You're given your I naught. You're given C, your damping coefficient. And note, the unit for C is Newton meter seconds per radian, and this applies to rotational system. Correct? K. And whenever I see K that's written in kilonewtons per meter, I would want to change that because some students, it would just write down 12.8 without looking closely at this unit. And then hence in the calculation, they'll make a mistake because they forgot that it's kilonewtons per meter. So I would write up front in this form. The length given as 25 centimeters. Again, I would like to change it into meters so that I don't make any mistakes later. And then area, 50 centimeter square. Again, change it into meter square. So I can't teach you how to change like centimeter square to meter square. If you can't do that, then you're on your own. So everybody knows that how we convert centimeter squared to meter squared. So the question asks us to show what is theta s over ts. Right. So this is also expressed not in this form, but I think it's given in words form. So you must be able to know what the question is asking. So what I'll do is to convert this into a free body diagram. So I know that this pressure is applying it to this point. So as we know, pressure is equal to force divided by area. So if I express this pressure, if I express using this pressure to know what kind of force is applied to this, it will be F is equal to A multiplied by PT. So that's the amount of force that's downward because the pressure is pushing it downward. So this one would be your rotary damper, and as you know, rotary damper, you have the moment that's applied to this pivot, and actually in your question, this is also called a torsional damper. So what you have learned is rotary or rotational damper. Just that there are just different ways to say the same thing at different textbooks. And in this case, in 1999, it was taught as torsional damper. Actually, rotational damper or rotary damper sounds more intuitive rather than torsional. So there's another spring that's applied over here. So we're going to sketch a free body diagram and look carefully how I go about it. So again, you have that point, and then this where you pivot this, pivot point O. And since I'm going straight into dynamics condition, so I'm going to perturb the crank that way. So you go down by this angle, and then over here by this angle. So the counterclockwise will be our convention, just like this. The counterclockwise is our convention. So the first force that I experience as this force over here is A et. Right? So these arrows are all meant for forces. And you have this rotational damper, or in the question it's called torsional damper. So when we have the crank that's going around in an anti-clockwise, you have the moments that's in the opposite direction. Right? So that moment would be C theta dot. And then you have your spring here that's going to be compressed. So if the spring is compressed in that way, then over at your crank, equal and opposite force. So this arrow is 1 this arrow. So that spring force, what you've got to know is Kx, but in this case it's not X because it's a rotary system. It's L theta. If you don't know why is it L theta, then your previous example will also be put there. So just by sketching this, maybe let me label. This is 2L, and this is L. And this is only true if you put this word on small angle theta. If you didn't write this or small angle theta, then I expect to see cosine theta over here. Okay. So if you don't write in that way, then you lose mark. How many marks is this free body diagram. This free body diagram is 2 months in that year for that question. So 2 months in your exam, actually each month in your exam is worth 1.66 months because there are only 3 questions. Each question 20 months. So altogether, there are 4 questions, you choose 3, right? So choosing 3, that means 20 months each. That's 60 months. So 60 months, we normalize it to 100 months. So each month that you get in your exam is 1.666. So every month that you lose over here costs you 1.666. Okay, first part. So after this free body diagram, let's sum up the moments around point O and equate that equal to I naught here dot dot. So you can see I stopped even writing dynamic conditions because that's going to cost me time. So I'm going to make it straight to the point. If you see a 0 over here, that means we're starting with a static condition. If you're saying I naught theta dot dot, that means this dynamic condition. So the first force, A, T, P. And since it's moment, force multiplied by the perpendicular length is 2L. And then the next one, this moment is in the opposite direction of my convention. So that means minus C theta dot, because it's already in moments. This circular round arrow means moment. The straight one means force. So it's already in moments. So I do not need to multiply anything. And then the last one, the spring force, is also acting in the opposite direction of my convention. So it's minus AL theta. And then it's just a force multiplied by the length L. So the whole thing equal I naught theta dot. So I can readjust a bit. I naught theta dot dot plus C theta dot plus 8L squared theta equal to 2L A dt. Right, just readjusting the equation. Next thing I do is to take Laplace transformation. Maybe before that, I'll just divide throughout by I naught. Divide throughout by I naught. And then I'll take Laplace transformation. Right, you can use other technique as well on this method. So Laplace transformation, I know that in this case here, the initial conditions for this setup is 0. So theta at 0 is equal to 0. And theta dot at time 0 is equal to 0. So taking the Laplace, I'm going to go straight into Laplacing and have all this as my coefficient. So Laplacing of this, because of initial conditions, they are 0, and I get S squared. This coefficient will stay S, and then that coefficient AL squared over I naught. So you can see that it's a very compact form. You can only do this if your initial conditions they are 0. So 2LA over I naught, and then ES. So if any of these ES or QS has been written as theta as, it is written as theta T or PT, after you have taken your Laplace, then you lose some mark. So that transfer function, theta S, GS, and then bringing everything to your right hand side and starting to substitute all these even numbers, all these even constants. I'll start to substitute it in. So that's 2, 0.25, 50 times 10 power minus 4 divided by 5. And then s squared plus 40 over 5 s plus 12800 multiplied by 0.25 squared divided by 5. So do that calculation, you get 0.005 105 over s squared plus 8s plus 160. So I have seen before students when they do the calculation for that numerator, it became 0.005 because many zeros and then it miss out that 110, and then the rest of the calculation became wrong. I've seen that before. So what's going to happen in marking is that you'll be penalized on that mistake, the mistake that propagates forward. Those will not be penalized, right? So those are still be marked. So you'll not get to see that until when you have that mistake in. But that's what it is here. Mistakes that you make initially, they are penalized. But the propagated error will not be penalized. Yeah. But if your following steps are wrong, then obviously you'll be penalized. So that's how it's marked. So this is your shown form. I think in your question it's written as 5 times 10 power minus 4, so the other thing. So if you get this, then you have 3 numbers. So part D, it asks for transient response. So I have told you before that I call it the time response. But what they all mean is this, what is the T. So particularly in the question it says step change in the pressure, and that's equals to 4 kilonewtons per meter squared. Now what it means is that this is a step input of 4 kilonewtons per meter squared. Right? A step change means a step input. So again, it's worded a little bit differently. We're used to saying step input, but it means step change. So what that means is that your PT would be 4 kilonewtons, so that's 4,000. 4 kilonewtons per meter squared, so I'm not going to write down the units. So if you take the Laplace of this, that means PS now becomes 4,000 divided by x. So what I'm going to do is to substitute PS into this part here and bring it to the right hand side. So what I'm going to have now, either S will be equal to, and you take 4,000 multiplied by 0.0005, you get 2. And then denominator, S squared plus 8S plus 160. So I'm going to solve it using Laplace transformation. So again, like I said, you can use other techniques as well. So in order to solve this, because of the denominator that's in this form, we'll form the partial fraction this that way. Okay, that's a partial fraction. In order to figure out that numerator, so the numerator here, numerator is 2, and then you do the cross multiplication, so A s squared plus 8s plus 160 plus ds plus c multiplied by s. Right, that's the partial fraction techniques. So let's multiply it in there. as squared plus 8as 160a plus as squared plus cs. So if you're able to get to this step, then in your marking scheme, this will get equal mark. So let's do the coefficient comparisons. The coefficient of s to the power of 0, that means a constant. The constant comparison is one constant here. This one is called s squared s squared s. So there's only one constant here. So that means a is equal to 1 over 80. Yeah. 1 over 80. So for the power s to the 1, to the power 1, that means this one and that one. So we already have a, so 8a plus c must be equal to 0. Why equal to 0? Because there's no s to the power 1 over at the left hand side. The coefficient for that is 0. So do a little bit of simplification. C is equal to 1 over 10. So the last one, comparing the coefficient of s squared. So you have s squared here, s squared here. So that is a plus b must be equal to 0 because there's no s squared coefficient over at the left hand side. So b will be equal to minus 1 over 80. So each of these, if you get it correct, doing the partial fractions and then finding out what is a, b, and c, you'll be awarded 1 mark each. That's a lot. So now we can put in our coefficients a, b, and c. So find theta s, and I can see that there's 1 over 80 inside, 1 over 80 here. B 1 over 80, C 1 over 10. So let me take out 1 over 80 coefficient, and the rest of it 1 over s minus s 8 s squared plus 8s and 160. So I couldn't do the inverse Laplace of this yet. So I need to break down this part here. So this is s and 8, and I need to convert the denominator into s plus something squared and then plus something squared. I need to do that. So in order to do that, you take this center coefficient here, 8. Take 8 divided by 2, you get 4. So in order to find out what is this number over here, you take 160 minus 4 squared. And what do you get? 144. Take the square root of that. 12, so this is 12. That's the technique. So now that you have that, we can further split this up because we still can't do an inverse Laplace of this. We can only do an inverse Laplace when you have this numerator here as s plus 4 or 12. So I can take s plus 4 over here and put the other 4 over the other side. So there's a 4 here. I couldn't take a Laplace transformation of this. I need a 12 here, and I could. So if I put a 12 here, then I'll put another 12 over here. So this I can simplify 1/3. So eventually, taking inverse Laplace transformation is your time response or in this case, is called transient response in a question. Will be equal to 1 over 80, that's 0.0125. You can still keep it 1 over 80 instead of converting it into decimal points. And then inverse of plus 1 over s is 1. And then inverse of plus of all this. I already know that as a common factor, e to the power minus 40. And then cosine 12t plus 1/3 sine 12t. So if you are able to do that, you get 3 months. So the last part there, it asks us to find out what is the damping coefficient C. The damping coefficient C at the following condition. So I'm going to write it in mathematical form. This straight line here, at the condition of the maximum point, maximum peak is less than 20%. It's asking us what is that. So if you recall, the sketch is going to be that way. So we know that your TP here is equal to pi over omega d. And TP refers to the time taken over here. Right? That's the peak time. TP. This time. And this axis omega t. But for tau t, right, there's a period of damped oscillation, that's 2 pi over omega d. So please don't be confused with these two. I've said it before, that students thought that TP is 2 pi over omega d. That's incorrect. And if you're worried about that, this TP is actually available in your data sheet. So I've also seen before that students did not really depend a lot on data sheet. It's already inside the data sheet. So if you're not sure, please refer to it. We have it there so that you don't have to memorize. Okay. So in this question, the maximum peak, right? Because it didn't say solve by first principle, so I'm able to use the formula that's inside your data sheet. E power minus zeta omega n dt, right? So at 20% or less, that is 0.2, will be equal to e to the power minus zeta omega n, and this TP over there will be pi over omega d. And omega d is omega n square root 1 minus zeta squared. Okay? So this omega n will cancel off. So 0.2 equal to e to the power minus zeta pi over square root 1 minus zeta squared. Then you can take ln on two sides. So that will give us minus zeta pi over square root 1 minus zeta squared. And I can bring that minus pi to this side, the left hand side. So I have minus 1 over pi ln 0.2 zeta over square root 1 minus zeta squared. So from here, some students actually don't really know how to solve. I've seen before it became like a one-page thing, it's all incorrect. So please know that the next step over here is to square both sides. Okay. In order to square both sides, this whole calculation over here, this whole thing is actually 0.15. 0.5123.
Desmond influence
Zero point
ministry.
five one two three. So squaring both sides to get that. So this part here, I'm going to bring it to the left hand side, so it becomes 1 minus theta squared. And then this part as well, I also had to see the mistake. Didn't forget to square this. Right. So if you forgot to square this, that means you get a quadratic equation. And then you get two values of theta. And that's completely wrong. So I'm telling you what are the common mistakes here. Don't let that happen to you. So let's expand it out. This is 0.26245. 0.26245 zeta squared minus zeta squared equals 0. So solve for it. You'll find that there's only one value, 0.4559. Zeta, there's 0.4559. What does that tell you? This system is less than 1, zeta less than 1, so it's an underdamped system. So he didn't ask you that. Great that you know. It's an underdamped system. So we haven't solved for what is the C, which is damping coefficient yet. So in order to solve that, I want you to recall that the general form for a second order system is given by this. And then usually this is equal to 0, but for your step force vibration system, this one will be 2L A over I naught dt. So that's your general form for a second order system. So what that means is that this coefficient here, if you compare it to what we had at the top, this will be equal to K L squared over I naught. And this part over here, this will be equal to C over I naught. So let's do the comparison in order to get us this C value. So omega n will be equal to square root KL squared over I naught. So that is 12800 L squared divided by I naught. So calculate that, you get this. So since 2 zeta omega n is equal to C over I naught, so C is equal to 2 I naught zeta omega n. So do the calculation. This is 2, this is 5, zeta is what we solved already, 0.4559 and 12.56. So that's 57.26. So if you miss out that units there, then you lose 1. So if you're not sure for C what's the unit, actually the question already gave you the initial part of the question. Yeah. Where C was 40 newtons meter seconds per radian. So sometimes you can find the units inside the question or other questions as well. So marks distribution for this one is 2 marks and that one will be 2 marks. So today we're going to start the next topic.
How does this become this? How does this whole row become 0?
What? No, because the second part has a different condition, that's why it's a different C. The second part is saying that now I have a new condition. Maximum peak is less than 20%. It's a new condition. Right. First part, there isn't that condition. Right. The second part is say that now we have a new condition. Your system now behaves with a maximum peak that's less than 20%. That's why what is the C level concept? So today we are looking at periodic motion. So the last time when we had for our setup, so if you remember, we had a setup.
Then become the new 2R3 minus 8 plus.
Oh yeah.
Okay. Thanks.
So we were saying that we had a case where we kind of like drop this weight on it, right? And that spring from this position extended a little bit more, right? Today's case is a little bit different. The kind of force that we're going to put in looks something like that. So I bought this from Daiso. So this is a pen. Right. Okay, you can feel it. Great. So this pen, actually, as I hold it in my hand, it doesn't really produce a lot of vibration. So what I'm going to do is that I'm going to put a little bit of off-center weight. So what that means is that I'm going to put this point on it.
Fly a lot.
Okay, so now that motor over here will be a little bit off-center. So what I mean is that I'll get this kind of vibration. Yeah. So you can see that this motor is actually vibrating in my hand, and it has a periodic movement, that means vibrating in that sort of frequency. Now, if you were to look at the kind of frequency of oscillation, if I were to oscillate this, which do you think would have a higher, well, there's no weight. Here, put some weight. Okay. Okay, how can you tell me which one would have a higher frequency? This one or that one? A or B? Which one has a higher frequency? A or B? Alright, this one will have higher frequency. It's vibrating this way. And this one is that way. Right? This one has a higher frequency. So what I'm going to do is that by itself, there's a certain vibration on this. So this vibration, if it's mixed together with this periodic force vibration, this one is periodic, right? So if I put them together, okay, you can see that the string is actually vibrating. This is one frequency. We call this frequency the input frequency because we put in that frequency. So out of which my system can also have another frequency. This one. Alright? So there are two frequencies in there. One is my input frequency, and the other one is my natural frequency. So please take note, later on you get to see two omegas. One is just omega, which is my input frequency, and the other one is omega n, the one that you know very well, that is the system natural frequency. Okay, so you get to see these two omegas. So the kind of response that you can expect from a system like that is that the final response, that if you were to sketch that, is going to be a mix of these two frequencies. And today, we're going to see what is that equation. Right? The equation of this response, we are able to know that. So you can imagine that equation must be quite a big equation. So let's have a look. Okay, thank you. So the force, the free body diagram that you saw just now, a little bit of damping, not a lot, but you have that kind of damping and a spring. And then this arrow over here, conventionally we were writing Ft, but in order to know the difference between a step force, thank you. So in order to know a step force, the difference between a step force and a periodic force, I'm going to use Pt to represent periodic force. So this one here, Pt. So this is my periodic input force. It's not step. Today we're talking about periodic. So the equation of motion for this, the equation of motion, mx plus cx dot plus kx. In our case here is not equal to ft but equal to pt. So the rest of it are pretty much similar to what we had before. So this pt here, it can be also linear. So if it's linear, then you go back to ft. So it can be step or ramp, but more importantly, this is periodic. So the periodic impulse. So this pt here actually has got an equation. This pt has an equation that's p naught sine omega t. So an example as what you have seen before, this can be caused by the unbalance in certain machinery or certain wind-induced vibration. So this part here, P naught, this is called the amplitude of this input. And then this is the omega I was talking about. So I'm going to write maybe in red color so that you are being reminded again and again. This is input frequency, radians per second units. Or in certain textbooks, you can also hear it as operating frequency, U1. So please note that if you will see omega, that omega means this is my input frequency. Input frequency means that is the force frequency, periodic force frequency that you insert into the system. So we'll be looking at a few topics later. So, under the harmonic motion or excitation, this system is forced to vibrate at the input frequency. So again, it's a forced motion, and then there's a new frequency that we put in. It's not a slash, but an input frequency. So later on, you get to hear a few things. You get to hear about a new term that's called frequency ratio. So I'm going to introduce to you frequency ratio. It's actually written as this symbol beta. So it's actually equal to omega over omega n. So omega is my input frequency. Omega n is the natural frequency of the system. Right? So I've shown that to you this time. So this is the same as writing input frequency over the system's natural frequency. And frequency ratio, this is dimensionless. There's no dimension to this. So later on, you get to hear beta a lot. So the thing is,